Well, thank you for joining, everyone. We're delighted to have our own Holly Hartman today. Holly is finishing her PhD, working with Kelly Kidwell and Matt Skipper in our department. She got her master's from University of Alabama, Birmingham before this. And Holly has won many awards as a student. And there are too many to list, but I'll probably hit the major ones that I thought. The Gertrude Cox Award, the Excellence in Research Award, as well as the Rackham Merit Fellowship. And I just heard she's probably being the commencement speaker this year as well. So congratulations, Holly. And so Holly's research interests are in clinical trials, health disparities, primarily in cancer. And we look forward to her talk today on small sample sequential multiple assignment randomized trials with continuous outcomes. All yours, Holly. Thank you.
Thanks, Vera. Thank you so much for that kind introduction. Yeah, the title is a bit of a mouthful. So I put down here some of my contact information. If you have any questions after the talk that weren't answered, you can email me. I also have some information on my website and then my Twitter handle as well. So I'll start with some background, going from the very basics for people who might not be as familiar with the clinical trial area, and talking about how that changes in rare diseases. So in clinical trials, the overall goal is to test treatments and to learn about their properties. And I'm going to be focusing on clinical trials that specifically compare multiple treatments to determine which treatment is the best to prescribe to patients first. So I'm not talking about dynamic treatment regimens at this point. I'm just talking about which treatment is best overall. So the general clinical trial procedure, you recruit patients, then you randomly assign patients to one of however many treatments you have. You observe some outcome, and then you might have a second randomization. You might observe a second outcome, and then you compare those outcomes between the treatments. In rare diseases, this first step is the most difficult, recruiting the patients. So if very few people have the disease, then finding these patients and enrolling them in a clinical trial is a big challenge. So in the US, a rare disease is defined as a disease that affects less than 200,000 people. And they're also called orphan diseases. And that's because historically, drug companies haven't been interested in researching and producing these drugs that they can only market to a limited number of patients. Fortunately, there was the Orphan Drug Act of 1983, and that helps provide some incentives for drug makers to start researching some of these treatments for rare diseases. And the number of treatments for rare diseases has increased since this act, although there is some debate about if that is due to this act or if it would have happened anyway. So some of the differences between general clinical trial design and rare disease clinical trial design, there are some statistical differences. So one of the big ones is that you can't rely on the property of large numbers, and that includes things like the central limit theorem. Since you don't have very many patients, you can't rely on those large numbers to balance out some of those issues. Additionally, since you have smaller numbers of people, then you have very wide variance estimates for your estimates. And then generally in rare disease settings, it's generally acceptable to make more assumptions or to have stronger priors. And this is because you have so limited information coming from patients that making prior assumptions or making stronger assumptions is generally acceptable. In terms of trial characteristics, it's difficult to recruit patients, like I mentioned before. But rare disease clinical trials actually have a very low dropout rate. Since there are so few drugs that are approved for a lot of these conditions, patients are somewhat eager to be on these clinical trials. They're just hoping for some treatment that helps them with manage their disease. And so there's actually a very low dropout rate in rare disease clinical trials. Overall, the big concern for rare disease clinical trials is that you want to get as much information as possible from as few patients as possible. So you're really trying to use those patients in statistical ways that gives you a lot of information. There is an international rare disease research consortium, and they published a list of recommendations. They had a lot of recommendations, including how to analyze the data, but then also how to involve patients in the trials as well. And I've just highlighted 4 here. So the first one that they recommend is using longitudinal data, and going along with that, using patients more than once. So if you can get repeated measures on a patient, then you have one patient, but you have multiple measures on them, and that's more information that you're getting from just one patient enrolled in your trial. A third recommendation they have is to not dichotomize outcomes or variables, and I'll talk about this in the next slide. But overall, when you dichotomize a variable, you lose information. And then the last recommendation that I want to highlight is using composite endpoints to better capture the patient experience. So this includes things like incorporating patient-reported outcomes into your outcome as a measure. And this helps because since there are so few treatments and a lot of patients have severe side effects with these new drugs that are being developed. And so having a patient-reported outcome as part of this composite endpoint can more holistically examine the treatment rather than just having something like how effective is it. So in terms of dichotomizing variables, there's a paper that was published by Dr. Altman in 2006 that I think highlights a lot of the issues that come from dichotomizing variables. So the first is that you lose information, and that reduces statistical efficiency. And that's the biggest one that's an issue for rare disease clinical trials. When you dichotomize, you lose information, and with a rare disease, you can't afford to lose information in your trial design. You might also increase the risk of a positive being a false positive when you impose this dichotomization. You might underestimate how much variation there is between the groups. And then individuals that are close to but are on opposite sides of that cut point are characterized as being very different rather than very similar. So if you have a variable that ranges from 0 to 100, say, and you have a cut point at 50, someone who has a value of 49 is in one group, and the person who has a value of 51 is in another group. And so they're being characterized as being very different when really they're only 2 points away. And so in that sense, this dichotomization strategy is actually imposing a level of false information onto your data. And then lastly, using 2 groups can conceal any nonlinearity that in that relationship between the variable and the outcome. And so if you had something like a U-shaped relationship between the variable and the outcome, you wouldn't be able to detect that if you just dichotomize them, because the averages of the 2 groups would look very similar. Really, you'd want to keep it in its continuous form to really capture that U-shaped relationship. There are also some practical issues that come about when you dichotomize variables. So the first one is that defining a cut point can be mathematically tricky. There are a lot of statistical methods that have been developed to optimize cut points, but that requires a level of skill and statistics knowledge prior to starting this trial that might not be feasible. And then additionally, it can be financially tricky to develop these cut points and validate these cut points because that requires a pilot trial. In rare diseases, there's already not a lot of funding to do this research. And so requiring a pilot trial can make a rare disease trial just financially infeasible. So in terms of what designs are used for rare diseases, one common one is a crossover design. So here people are randomized to one of 2 treatments. And then after some time point, the people switch to the other treatment. And there can be a washout period here where people are not on any treatment, or they could just switch right over to the next treatment. But overall, they're starting on one treatment and then switch to another treatment. This design gets a little bit more complicated if you have more than 2 treatments. Here is an example of how a trial could run with 3 treatments. I only have 3 arms here, but practically there could be 6 arms because you could also have A, C, B, or B, A, C. And so the three arm trials or 3 treatment trials for crossover designs can get a little bit more tricky. They also take a longer time because now you have 3 stages rather than just 2. One recent development in rare disease clinical trials is this snSMART design. So here, patients are randomized to one of 3 treatments, and then an intermediate outcome of a response or non-response is measured here. If the person is responding to the treatment, then they stay on that same treatment. If they're not responding, then they're re-randomized to one of the remaining 2 treatments. And one of the benefits of this trial design, as opposed to the crossover design, is that if a person finds a treatment that's working for them and is treating their disease, they can stay on that same treatment. And if that treatment isn't working, then they get another chance to try another treatment for it. So in this sense, this is beneficial to the patients because unlike the crossover design where they have to switch on to a new treatment, even if A was working, here, if they find something that works, they can stay with it. So this has some benefits from the patient perspective as well. However, one drawback is that this does require this intermediate variable of response or non-response. There is one ongoing snSMART design, and it's called Regimens, and this is a trial for isolated skin vasculitis. And in this trial, there are 3 treatments that have been previously standardly routine prescribed for isolated skin vasculitis, but none of them are considered standard of care. And so there's no control arm in this setting. So this is the basic trial design for Regimens, and all 3 of A, B, and C are active treatments. And they're all being compared to see which one is the best. So now I'm going to show my proposed design that allows for a continuous outcome instead of that binary response and non-response. I'm going to talk about how we analyze the data and then some of the simulation settings that we examined. So this is the design that I proposed. This is a snSMART with a continuous outcome. So it starts off similarly. Patients are randomized to one of 3 treatments, A, B, or C. And then instead of a dichotomous outcome in the middle here, it's a continuous outcome Y1 that's measured. And then based on this Y1 value, patients are randomized to one of the 3 treatments again. So there's a mapping function that takes this Y1 value, this outcome, this intermediate outcome, and maps it to a probability of staying on the same treatment. So this mapping function takes that Y value, maps it to a value between 0 and 1 inclusive, and that's the probability of staying on the same treatment. So in this setting, better outcomes of Y1 should map to values that are closer to 1. So if a patient is doing really great on their treatment and they have a really great outcome, then they have a really high probability of staying on that same treatment. And so moving forward, when I'm talking about this, we're going to assume that higher values of Y are better, so the higher the better, and that Y approximately ranges from 0 to 100. And we selected this range, this approximate range, to mimic what a patient-reported outcome might look like. A lot of patient-reported outcomes are standardized measures to be between 0 and 100. So here we have this approximate range here to mimic a PRO. There are a lot of options for the mapping functions, what you can select to take that intermediate value and map it to a probability. One option would be a linear function between the minimum and maximum values of Y. So here is just a linear function between the minimum and maximum. You can also take this function and modify it with powers if you want to change the distribution of how many people are staying and how many people are switching treatments. You can also impose different minimums and maximum values to have different properties. So if it's feasible for a person to receive a very, very low score, but if it's below, X, then you definitely don't want them staying on that same treatment. It just wouldn't be ethical to have them continue on that treatment. You could set a different value from what is the actual minimum. And then likewise, if you have some value where it's just amazing that this person is doing so well, you can't imagine switching them off this treatment, you could impose a maximum value here as well. Theoretically, though, you could use any cumulative distribution function. Since that's monotonic, it increases as Y increases, and higher values of Y are better here. And it's bound between 0 and 1. So you could use feasibly any CDF that you wanted. So here I have an example of some mapping functions. So over here is the distribution of outcomes that you would expect in your patient population. So for example, this one, you have kind of a uniform distribution. And then over here, you have the possible mapping functions. So for a given Y value on the Y-axis here is the probability of staying on the same treatment. So if you have kind of a uniform distribution, you expect people to be kind of all over the map with their outcomes. You could use just that linear function here, or you could do what I mentioned before and impose some different minimum and maximum values and do linear in between those values. If you have a normal distribution, you could do a piecewise function where you have something that curves up to 1 and then flat if it's higher than here, or you could also do that linear function again. If you're expecting to have a skewed distribution, then you could select something like this, which is a smooth square root curve between 0 and 1 across the range of Y. Or you could do a piecewise function where you have an imposed maximum and it's flat after that. So there are a lot of different options for these mapping functions, and it's quite flexible. In terms of how we're going to analyze data from this trial, we chose to use Bayesian methods so that we can jointly analyze data from both the first and second stage outcomes. So here we have a multivariate normal likelihood. We have our outcomes here for the first and second stage. Our first stage mean is only dependent on what treatment they received in the first stage. And our second stage expected outcome is based on both the treatment from the first stage and the treatment from the second stage. And then the covariance matrix is a function of the sequence of treatments that the person receives as well. So it's based on the first stage treatment and the second stage treatment. Oh, whoops, this slide got messed up. So overall, the goal is to estimate some beta J parameters. So it's a little difficult to see here. Maybe if I do. There we go. So our overall goal is to estimate these beta J parameters. So this is the mean model for the first stage outcome. And it's basically just the beta parameter for that, for whatever treatment the person receives. So if the person received A, then the expected outcome is just beta A. So our goal is to estimate that first stage treatment effect for all the treatments. And so that's put into normal language, and then statistically, we're estimating the beta J parameters. So the second stage mean model is a little bit more complicated. So these first two terms here are a weighted average of the first stage treatment effects for the treatments that the person received in phase 1 of the trial, and the treatment that the person received in the second stage of the trial. And they're weighted by these alpha parameters. And I'll discuss a little bit more about these alpha parameters later. But overall, these first two components are just a weighted average of the treatment effects for the first stage treatment and the second stage treatments. And if the person stays on the same treatment, then there is a bonus effect that the person has. So if the first and second stage treatments are the same, then they have this additive effect of alpha 3 here. This is an example of one of the stronger assumptions that people make in rare disease trials. So in discussions with the collaborators for that Aramis trial, they allowed us to make some of these assumptions, such as the first stage treatment having some effect on the second stage outcome, but it mostly being the second stage treatment having an effect on the second stage outcome, as well as this cumulative effect of a person staying on the same treatment. So the covariance model that we used, we have one covariance matrix if a person stays on the same treatment. So in that case, we would expect the second stage outcome and the first stage outcome to be highly correlated because the person is the same person and receiving the same treatment. And then we have a different covariance matrix if the person switches treatments. We would still expect some relationship between the first stage outcome and the second stage outcome because it's still the same person and their body still processes things the same way. but we wouldn't expect it to be as high of a correlation as if they were receiving the same treatment. For the priors that we impose onto our model, we have a relatively non-informative priors for those beta J parameters. They're normally distributed with a mean of 50, so it's centered between our approximate range of Y, with a pretty wide standard deviation. Then for our covariance matrices, we have an inverse Wishart prior, and that's just the cognate prior for a multivariate normal distribution. For the alpha parameters, we set up our priors to meet some constraints that we have imposed. So the first constraint that we imposed is that alpha 1 and alpha 2 sum to 1, and that both are positive. So this means that that first segment of this second stage mean model is a true weighted average. The weights sum to 1 and they're both positive. The second constraint that we have is that alpha 2 is greater than alpha 1. And this means that the second stage treatment that the person received has a greater influence on the second stage outcome than the first stage treatment. And this makes sense because the treatment that they receive in the second stage is going to have a larger impact on the most recent outcome. And then our last constraint that we have is that this alpha 3 parameter, which is the bonus effect for staying on the same treatment, is positive or non-negative. So this means that there's no harm that comes due to staying on the same treatment. And so the priors we set up to meet these constraints were as follows. So alpha 1, we have a uniform between 0 and 0.5 constraint. And this satisfies both the first and second constraints. So we don't have a prior for alpha 2 because we can solve for it in this equation, and then alpha 2 is necessarily larger than alpha 1. And then for alpha 3, we have a folded normal distribution, and this requires that, and this sets alpha 3 to be positive. In terms of how we simulated our data, I'm going to be presenting the results where n equals 30 in each trial arm, so for a total of 90 patients. But we also explored if n is 15 or if n is 100 as well. And this is in our paper, which is published in Statistics in Medicine. We simulated 2,500 trials for each setting. And then we did the Bayesian analysis as described. We also had 1,000 burn-in and 1,000 MC-MC repetitions. And then just as a reminder, our goal is to estimate those beta Js, the treatment effects on the first stage outcome for all of the treatments. So how we actually generated the data was slightly different from the setup. So we have our first stage outcome being conditional on our treatment effect, and we distributed that to be normal with that first stage mean and then the standard deviation. And then we assigned if a person should stay on the same treatment using a mapping function and then a Bernoulli distribution with that probability in there. Then if a patient does not stay on the same treatment, then we would assign a new treatment using Bernoulli with a 50-50 probability of staying on the same of each treatment. And then the second stage outcome was generated using this normal distribution. And this is just the conditional normal distribution for a multivariate normal. And this is conditional on the 2 treatments that the person receives, and then also the first stage outcome of that person as well. So here's how the process looked practically. So we randomly assigned people to one of these 3 treatments. We measured their Y outcome here, and then we randomly assigned if they should stay on the same treatment or if they switched treatments. And then if they were switching treatments, there was a second randomization here to decide which treatment the person was on. So in terms of the mapping functions that we looked at, we limited all of our mapping functions. We imposed Y minimum of 0 and the maximum of 100. So if a person had an outcome less than 0, then they were definitely going to switch treatments. And if they had an outcome that was greater than 100, then they were definitely going to stay on that same treatment. And then we looked at 3 different mapping functions indicated by these MF1, MF1/2, and NMF2. So the first one was just a linear function, just dividing the outcome by 100. The second one, we took a square root of that first function, and this is a mapping function that would allow more people to stay on that same treatment. And then we looked at if we squared that function, and this is a mapping function that would have more people switching treatments. And then we came up with some comparable dichotomized outcomes. So we had a cutoff at 30, where a lot of people, if it's greater than 30, they would be staying on the same treatment. And if their outcome was less than 30, they'd switch. And then we also had 50 and 70. So 30, we would have a lot of people staying on the same treatment. So this is sort of similar to the square rooted mapping function. 50 is about 50-50, so it'd be similar to this MF1, and 70 would be similar to MF2. We also compared these designs to a single stage design. We are hoping that there's a benefit by having this joint analysis where we have both the stages of outcomes, but we wanted to ensure that there was a benefit over a single stage design as well. In terms of the actual values that we set up here, our covariance matrices, we had a shared standard deviation across both stages and all treatments. And then we had our correlations here. So the correlation, if you stay on the same treatment, was 0.8, and if you switch, it was 0.3. And the standard deviation was 20. And then for our alpha parameters, so alpha 1 and alpha 2 were those weighted averages. So alpha 1 is 0.2, alpha 2 is 0.8, and then the bonus effect if you stay on that same treatment was 5. And then we had the beta J's vary by scenario, but the actual range was between 20 and 80. So they were all within that 0 to 100 to reflect possibilities from a PRO. We also explored the possibility of assumption violations. Since this is a rare disease setting, we did have some strong assumptions, and so we wanted to know how these models worked when there were violations in those assumptions. So from here on out, I'm going to call the ordering of treatments that the patient received the treatment-specific pathway. And so that would mean that would be an example of that would be a person received A in stage 1 and B in stage 2. So one of the assumption violations that we explored was that the second stage mean was fully dependent on the treatment-specific pathway. So instead of it being that weighted average that I talked about, it being fully dependent on the combination and timing of those treatments. The second assumption violation that we explored was that the standard deviation was dependent on the exact treatment that that the patient received. We had a shared standard deviation here between all of the treatments, and so we wanted to see what would happen if that wasn't the case. The last assumption violation was that the correlation between the first and second stages outcome also depended on that treatment-specific pathway. So instead of it just being highly correlated if you stay on the same treatment and not very correlated if you switch treatments, having it really depend on the exact combination of treatments that the person received. So something like this might happen if treatments A and B, for example, have very similar biological mechanisms. So potentially if one is a generic for a drug, then they would have very similar biological mechanisms. So they would act on the body in the same way. And so you would expect high correlations between those two treatments, regardless of if you switched between them. So here are all the scenarios that we looked at. We have our beta J parameters here. First, we have them being centered right in the middle of the range that we expect, 40, 50, and 60. In scenario 2, we have the betas being lower in the range, 20, 30, and 40. And in scenario 3, we have them being a bit higher, 60, 70, and 80. Then we explored all of the violations and assumptions individually in 4, 5, and 6. And then we combined all of the different assumption violations in the remaining 4 scenarios. So now I'll go through the results that we had and talk about some of the patient outcomes as well. So here we have the results for a single stage design versus our multi-stage design. here we have the actual root mean squared errors, and then we have a ratio of the root mean squared errors relative to the single stage design. And you can see that regardless of which mapping function we use and regardless of which scenario we're looking at, there's an improvement of using the multi-stage design, our design here with the mapping function over the single stage design. And that's indicated by these RMSE values all being less than 1. So there's some improvement in the bias or the variance that is improving our trial design and our efficiency overall. Next, we compared our design to the design with the dichotomized outcome, where we had the cutoffs at 30, 50, and 70. So the blue boxes here indicate the mapping function designs, and the orange boxes indicate the dichotomized outcomes. And then we have the average bias for the beta parameters for all of the different trials that we looked at. And so ideally, we want these boxes to be close to 0 and very compressed. And you can see that the mapping function does fairly well across all of the scenarios, and regardless of which mapping function you're using. There's relatively little bias, and the estimates are all are not too far spread out. When we move to looking at the dichotomized outcome, we can see that the dichotomized outcomes that had either had a high bias but very little variance, or they had very high variance but very little bias. And you can see that which dichotomized outcome has the least amount of bias but the highest variance depends on which scenario we're looking at. So the bias actually depends on which dichotomized outcome that you're using. And we also found it interesting that the dichotomized outcome that had the highest variance was also the one that had the median treatment effect. So here it's the dichotomized outcome of 50 in scenario 1, dichotomized 30 in scenario 2, and dichotomized outcome of 70 in scenario 3. So we wanted to dig into why that was happening a little bit. So we looked at the percentage of patients that were staying on these same treatments in this trial design. And so here, how this table is set up is we have our mapping functions of 1, 1/2, and 2. And then we have our dichotomized outcomes of 50, 30, and 70. And so 50 kind of corresponds to 1, 1/2 to 30, and 2 to 70. And so in the most extreme case where we have a dichotomized outcome where a lot of people are switching treatments and we have these very low outcomes in scenario 2, we only have 3.2% of people that are staying on the same treatment. And then the other extreme here is where we have our dichotomized outcome of 30. So a lot of people are staying on the same treatment, and we have our very high average outcomes here. And in this case, 96.8% stay on that same treatment. And then in the corresponding mapping function settings, we have high values or extreme values, but not quite as extreme. So 13.5 as compared to 3.2, and 82% compared to 97%. And this is causing issues where we have a great number of people that are staying on the same treatment or a great number of people that are switching treatments, because a lot of our parameter estimates depend on if a person stays or switches on their treatment. So that alpha 3 parameter, for instance, we can only estimate that if we have a decent number of people that are staying on the same treatment. And then same for the covariance matrices. That depends on if a person stays on the same treatment or if a person switches. And so in these extreme cases where we have a poorly selected dichotomized outcome, we're not necessarily exploring all of those treatment pathways. When we fixed the variance and that alpha parameter, and we didn't require them to be estimated, and then we looked at different dichotomized outcomes, we can see that when everything that depends on exploring all treatment pathways is fixed, the bias and the variance is consistent regardless of the dichotomized outcome. So we don't see that trend where the dichotomized outcome bias depends on which cutoff we select. So that was the reasoning for why that was happening. Then we looked at our model assumption violations. So here I have the different scenarios across the top. And then down here I have the beta estimate for each. And then I have the beta, the 3 betas. So you can see in scenario 4, 7, 8, and 10, the beta alpha parameter has a very high bias. And these are all the scenarios where the mean model assumption was violated. And the reason that the beta A parameter is the most affected is that that was the one that deviated the most from our assumptions. So our model is not very robust to assumption violations in the mean model. And then in scenarios 5, 7, 9, and 10, you can see that the variance around the estimates depends a lot on which beta you're estimating. And those are the scenarios where the variance estimate, when the variance depends on which treatment the person is receiving. So you can see that treatment C had the highest variance, and so it does in our estimates as well. And then in scenario 6, this is just the correlation assumption violation on its own. And you can see that our model is actually fairly robust to that assumption violation when it's not combined with any other assumption violations. So now that we've looked at the statistical properties of this design, we wanted to look at patient outcomes. So for patients that are enrolled in this trial, how are they faring? We have good statistical properties, but we wanted to make sure that we weren't adding additional harm to patients enrolled in this trial by doing this type of randomization. And you can see, again, the blue boxes are for the mapping function and the oranges are for the dichotomized outcome. You can see that the patient outcomes are fairly consistent regardless of which mapping function we use or which dichotomized outcome we use. They only differ by scenario, and that's just because the average outcomes differ by scenario as well. So we're not adding additional harm to patients by doing this new trial design. So overall, this is a new clinical trial design that allows snSMARTs to proceed without a binary tailoring variable. We are getting away from that dichotomization. There wasn't any additional harm to patients that were enrolled in this trial. We had lower bias and higher efficiency than a dichotomized outcome design or a single stage design. And this design also meets many of the requirements that were suggested by that International Rare Disease Consortium. So now I'm going to talk a little bit about the future directions for this research in the remaining time that I have. So now instead of trying to estimate which treatment is best overall, I'm going to be looking at producing dynamic treatment regimens. And so a dynamic treatment regimen is something like this. Give a patient treatment A. If X, then continue A. If not X, then give B. And so this is a tailored sequence of treatments based on some intermediate event. So this X could be something like if they're responding to the treatment or if their biomarker is greater than this. It just has to be something that is either yes or no kind of option. So SMART trials have been used to estimate these DTRs. They have a very similar design to that snSMART design. But their overall goal is DTRs. And these also require predetermined dichotomized intermediate outcomes. And the most commonly used way to analyze this data is using generalized estimating equations, or GEE. So this is an example of what a SMART might look like. You're randomized to one of 2 treatments. If you respond, you stay on that same treatment. If you don't respond, then you're re-randomized. So I propose a new design, and these new designs will have a set of treatments that are for favorable outcomes, and then a set of treatments that are for less favorable responses. So if a person has a favorable response, then a treatment that they could receive might be staying on the same treatment. It might also be switching to some sort of maintenance therapy. And then treatments for less favorable outcomes could include switching to a different treatment altogether, or maybe increasing the dose of the same treatment. So I'm going to present some potential schematics for some of these designs. And I used unique letters for all the possible treatments, but with this in mind, there could be some overlap in the treatments. So this would be the most basic design where patients are randomized to one of two treatments. This intermediate outcome is measured. And then people are re-randomized to either one treatment if they have a favorable response or one other treatment if they have a less favorable response. This design has two possible outcomes for patients who do not have a favorable response here, but otherwise it's the same as before. And then here we have a setting where there are two possible treatments for if a person has a favorable response and two possible treatments for if a patient has a less favorable response. And so there are a couple of ways that we could incorporate mapping functions into these designs. So one option for a mapping function would be to incorporate the intermediate outcome as a continuous measure. So this would be like a linear function here. And we use the terminology tailoring function in this setting because the SMART literature talks about tailoring variables as being that intermediate outcome, and that's also common in DTRs. So here we have a tailoring function rather than just a tailoring variable. Another option would be to incorporate it as a dichotomized variable using that an indicator variable, and this would be similar to a tailoring variable. And then the last option would be to not incorporate that intermediate outcome at all, and you would just use some fixed probabilities of each treatment. So there are a couple of different ways that those trials could proceed based on which tailoring function you select. In terms of methods for how you would analyze this data, you could look at Q-learning, tree-based regression learning, or outcome-weighted learning. And the reason that we have to change how we're analyzing this data is because in the GEE framework and what's been commonly used to analyze SMART data, they assume that you already know that tailoring variable. You already know if X, then stay on the same treatment. But in these new designs, you have to develop that tailoring variable and the DTR all within the same framework. You don't have the benefit of already having a pre-selected dichotomizing variable as well. We also looked at these methods because these are what are used to produce dynamic treatment regimens from the observational literature. So when you're trying to develop a DTR from observational data, then these are the commonly used methods. So outcome-weighted learning, this is a method that was originally designed to estimate patient outcomes and develop individual treatment plans by weighting patients proportionally to their outcome. And it uses the framework of support vector machines. There have been a couple of expansions to this method, including multi-stage treatment plans and DTRs. And it's also been expanded to multiple treatment options and this method is called sequential outcome-weighted multi-category learning. But there isn't literature that currently features both multi-stage and multi-treatment analysis, although the methods for sequential outcome-weighted multi-category learning do discuss that as a possibility. Q-learning is a method that is used to maximize an outcome based on a sequence of decisions. So you kind of work backwards in Q-learning. You start by optimizing the decision rule to maximize the second stage outcome, and then you select the decision rule to maximize that first stage outcome. And so in order to account for our randomization schemes here, we'd have to use inverse probability weighting. The last one is tree-based reinforcement learning, and this is a goal, and this is a method to develop DTRs based on tree regression. So you have measures of node purity, and you create splitting rules based on those based on improving those measures of node purity. And you also have some restrictions on maintaining the node size. So those are the methods that we're going to explore for the SMART DTR development with tailoring functions. Another possible extension that I see for this research is in umbrella and basket trials. So umbrella and basket trials use biomarkers to group patients. So there are basket trials where people are grouped by some marker, and then there's sub-studies here. And then in umbrella trials, there are markers to define which sub-study each person is going to go into. However, a lot of times those biomarkers are continuous variables that have been previously dichotomized. And so if we can develop methods that allow us to keep those biomarkers as continuous measures and study the effects of these treatments based on those continuous measures rather than by discretely binning these people, then that could be a very effective way to conduct these trials. It also eliminates a lot of issues that can happen when people are misclassified based on their biomarker, or if people are positive for multiple biomarkers. So if you're powering these studies based on a continuous interaction rather than a dichotomized interaction, then that also may reduce the sample size that's needed. So this is just basically what I've already said. And then in terms of other possible extensions, you could also explore continuous treatment dose, or you could also use a utility measure as an outcome. So I wanted to make sure that there was time for questions. So thank you very much for inviting me and listening to this talk. I hope you all learned something. And I apologize, my headphones died during that talk. So I'm just going to switch what headphones I'm using real quick.
Wonderful. Thanks, Holly. So I don't see any questions on chat, but if there are questions, anybody can unmute and ask a question.
Hello?
Yeah, I can hear you, Holly.
Okay, great.
So I had one while folks are mulling over. So in terms of from a practical perspective, if we had to provide some considerations for choosing the mapping function, for designing such trials in the future, what sort of what sort of aspects should they consider, when you have a continuous outcome? And the second part of the question is, did you reanalyze the trial data, or this was just from a design perspective?
Yeah, so I'll answer the second question first. So this was just from a design perspective. So there isn't currently any trial design that has used this design. So we weren't able to actually analyze any data like this. But it was motivated by that Aramis trial. But since this is a new design, there hasn't been a trial that has been run with this data, or done this way. So we don't have real data to look at. So this is purely just a design paper. And then for your first question about recommendations for mapping functions. So we saw that there were good properties when about half the patients stay on that same treatment and about half switch treatments. So if you can find a mapping function that kind of has those properties where you would expect about 50-50 to be staying and half to be switching, then that would be good. But we also saw that this was fairly robust to whichever mapping function you selected. Even when the mapping function and the actual outcomes were very much mismatched and we had a lot of people staying on that same treatment or switching treatments, it was fairly robust to that. So although I would suggest trying to get it to be a 50-50 split, it seems like there's a lot more room for error than if you're using a dichotomized outcome.
Thanks. Jeremy? Yep.
Hi, yeah, very, very clear, Holly, very nice. So I guess two questions. The first part, can you talk about coverage rates of uncertainty intervals? And then the second part, I was curious, right? So you made a very compelling argument for, using Bayesians and priors and inserting information, but all those methods like Q-learning and trees, they're very non-parametric. I mean, they sort of go the opposite direction, right? So can you thought about getting your sort of informative priors into the DTR stage of your research?
Yeah, so unfortunately, I didn't put the coverage rate tables in as bonus slides, but the coverage rates showed similar things as what I just showed before. The coverage rates were fairly good for the mapping functions, regardless of which mapping function you selected in which scenario, but they were a lot different for the dichotomized outcomes. Either the credible intervals for some of them were just very, very wide, and they had very high coverage, higher than we would expect nominally. And then, since there was bias in some, they had low coverage probabilities there. So we did look at that as well. And then in terms of the methods that I was going to look at, there's another method that I would be interested in exploring that came out of Peter Thal's group and one of his postdoc that's now at Minnesota, whose name I'm blanking on, called Bayesian machine learning. And I think that that would be a very interesting addition to these groups of analyses. And that is basically looking at tailoring sequences of treatments using Bayesian methods, but kind of in a machine learning framework where it's kind of tree-based or kind of similar to like a Bayesian Q learning method, I would say. But those methods haven't been explored for, I think, sequences of treatments. They have been explored for just optimizing the single treatment, I believe is the current state of that literature. But I have been looking at that as another possible option for another method of analysis here.
You're ready? You just want us to throw out questions?
I'm ready.
Okay, Holly, this is Tom Braun. Nice talk. I had a question about, sort of related to Vera's question, is you worry about the correct exponent that you put on this mapping function, right? I'm wondering if you could adaptively adjust that through the data. If there's a realistic assumption you'd have enough data to figure that out, maybe that you should start moving more people around or not?
Mm-hmm. Yeah, I didn't look into that, but that's an interesting possibility of adapting it, that power function. We did, in our discussion, we talked about potentially having it be adaptive based on the outcomes that patients were having rather than the trial characteristics. So adapting that function to be not based on just the individual's outcome, but based on the individual's outcome and then also everybody else who's already completed the first stage, and then using that kind of as an adaptation method. But I haven't explored it, but I think that would be a very interesting use of this mapping function, especially because you could then start exploring how you're weighting the different effects. So you could even have like a component for making the trial characteristics look nice, and then one component being the prior outcomes, and then one component being the actual individual's outcome. And you could come up with some very complicated mapping function to incorporate all of those properties and then come up with outputs there. So one of the nice things about this is that that mapping function is so flexible. So when you start getting into an adaptive concept, you have a lot of options with it.
So, Holly, can I just ask, so maybe it's clarification. You talked about much better than a binary outcome. You got better estimates of betas, but I guess I was a little confused because if you have a binary outcome, betas don't mean the same thing, right? So I don't know what exactly you meant by that.
So in this setting, the outcome is actually being analyzed as a continuous measure, but for the trial to proceed, it's being dichotomized just as that trial property. So you're still analyzing it as a continuous variable. It's just how the trial proceeds.
Okay.
And that's what they're doing in Aramis, I believe, as well. They have a composite endpoint that they're looking at, but the trial, in order to proceed, needed a dichotomized response definition.
Any other questions? I actually had one, Holly, about when you mentioned the extensions to umbrella trials. So in terms of bringing in the biomarker-based trials, so would these biomarkers, like your Y1 comes after the first stage of treatment, right? So you're expecting the biomarker, the treatment to change the biomarker Is that the setting, or these are, we would consider baseline biomarkers that are usually right now is the state of the art to use baseline biomarkers of mutations to assign treatments, right? Like, for example, these multi-arm trials like the I-SPY and the GBM Agile trial. So how do you like sort of maybe parse out differentiate the two and where the utility of these designs will, be?
Yeah. So I have primarily thought about this in terms of a basket trial where you're looking at the biomarker ahead of time, and it's just you're using that biomarker to then put people in their baskets. And so I've been thinking about it in that context. And so then it wouldn't be a multi-stage design. It would be like you're using a baseline biomarker to assign that treatment. But then if there's a way to use a continuous biomarker to assign that treatment, then that would be kind of the extension that I'm proposing. So rather than using that dichotomized biomarker, which could be something like, some measure of protein in the blood or something along those lines, keeping it in its continuous form to assign treatment, and then also to use that continuous interaction to power your study as well, rather than it being a dichotomized interaction.
Got it.
So I think I've seen people suggest that trial they have an indifference range for a biomarker in the middle. Within that range, they randomize to one of the two groups, right? But above a threshold, it's all group A. Below a threshold, group B, and in the middle, they randomize them. And I think the rationale I've seen is so they can help sort of determine the biomarker function, if you like, as sort of an adaptive study. I don't know, it's quite related to what you're talking about, but it's somewhat
Yeah. Yeah, so it would be pretty similar to that, but instead of it being, equally split for that randomization, it would be a function of whatever that actual value is. So instead of it being just totally randomized, and another possibility would be instead of having it be, the low values, the intermediate values, and the high values, having everybody be still on that continuous scale here to do it more like that. And then there's also issues when you have that intermediate group where if you're looking at multiple biomarkers, it can get a little bit complicated with how you're assigning treatments as well. But yeah, it would be similar to that intermediate value being randomized again, or randomized between the different sub-studies, but it would be hopefully more flexible.
I think the I-SPY trial tries to do something similar, right? If I'm not wrong, in breast cancer, they use the biomarker to re-randomize or adaptively randomize.
Yeah.
Not sure re-randomize on that. Any other questions? As we are right on the clock at 4:30. So thank Holly again for an excellent talk. Very clear.
Thank you so much for having me.
Thank you. Great job, Holly.